Alright, let's get started. This is the first session of a very long series of courses. So I want to address the problem of, because we're talking about FP and JavaScript. So I think it deserves the explanation of why those two things together and why the individual things here. First, the short one is for JavaScript. Why we're using JavaScript in this series of courses. It's a very unfortunate kind of choice because it's very popular and many people use it to a point that I think it's going to take the world and cause lots of bugs and money. Because of that, I think JavaScript developers can benefit from functional programming way. So that's the reason I picked JavaScript. So why FP? Here's a bit of a long sales pitch for you. I want to address, I want to mention three things in FP, and I'll talk to you about each one of them. So first is composition. Hopefully I spelled that correctly. Yeah, composition, and there's types and function, obviously. Okay. Let me start with composition from a perspective of system theory. Assume no one here understands system theory. Very good. Yeah. So first, I need to explain what is a system. We write system every day. You might not agree with me. Let me convince you though. When you write a function, you're basically writing a system. Or you're writing a design, architecting a platform, it's more obvious that you are looking at a system. You're designing a system. A system, by definition, partially, is a whole, not a whole on the ground, but spelled with a W, that whole, yeah, WH, yeah. Consists of parts, and it has certain characteristics, attributes, and properties. And there's two of them are very important. One is the individual parts cannot reflect by itself, cannot reflect any of the property of the system. It is only the collective interaction with parts will reflect the property of the system. It's very easy to demonstrate. For example, human body is a system. Yeah. Your hands can, you can write, but your hands cannot. It may sound absurd, but it's very easy to prove because if you chop off your hand, put it on the table, it doesn't write itself, right? Yeah. Similar idea, you have a life, your organs doesn't have a life. Yeah. So it is this notion that every single line of your code is the parts of the function. They become a system in the end. Bring up the characteristics of the function itself. You take an input, it spits out something for you. None of the line itself can reflect that. It's only the collective lines. It's very easy. It's the same in simple in like platform design architecture. So that's one, which brings to us the second point I want to make. So every single part of those systems are interrelated and interdependent. What does that mean? Let me give you another example.
let's say you want to build the best car in the world.
And your approach would be this. Let's say there's 500 different models of cars produced this year. And you buy a you lease a big warehouse. You buy one of each, 500 cars comes in. And you hire the best engineers in automobile, for example. And you start asking questions to say, who has the best engine? Supposedly, you come back to say, Mercedes has the best engine. You may not agree with me, but let's go with this example. And you take the engine out of one of the Mercedes car. And you ask another question, who has the best battery or belt, like this. And you take the individual parts from those vehicles and you put them together. Do you have the best car in the world? No, right? You don't even have a car because the parts doesn't fit. So all the parts needs to be related to, in a sense, that interact with other parts of the system. Human body is the same. You have a heart problem, maybe it's because your lung, your circulation, or your foot. Who knows? So this interdependency in programming, or in functional programming, is called composition. So if you can look into your code or entire platform into a systematic kind of approach, then system theory tells us that interaction is always the most important thing inside a system. It doesn't matter how individual parts work and work very well, it doesn't really matter. It's the interaction and the relationship between them which matters most. From that perspective, I think functional programming addresses this in a very good way, comparing to object-oriented programming. The emphasis is on consistently. What does that mean? In object-oriented programming, you have design patterns. Let's name one. Dependency, sorry.
Factorial dependency injection.
Yeah, cool. So that is for loose coupling.
Yeah.
Right? Yeah. So most people, when talking about those patterns, they talk about loosely a lot. I want to say coupling is, the noun here. Right? You need to couple to do things. Whether it's loosely or tightly, it's just the design pattern itself. So that kind of coupling is composition as well. It's the relationship and the interaction between different objects, different methods, things like that. And you can name them, like in object-oriented programming, you can name many of them. And when you're looking into individual patterns, you rarely find a relationship between them. They all solve very, very particular kind of limitation of the language itself. Well, I'm happy to be proved wrong, but that's what I think. But in functional programming, the difference is every single level of composition is bound by a very simple idea. The idea of those three things. So let me demonstrate a little bit of them. So when we talk about functional programming, we have to talk about category theory. So let me just introduce a little bit to get the idea across. So what is a category? I'll demonstrate using a graph. Is a circle. This is much better. Okay. So I teach my daughter to draw. It's always a circle first. But yeah, so it's a category when you have like a egg, something like that. It's a category, and we have dots there, which we call objects. Nothing to do with object-oriented programming. It's just, you can call them thing or dot.
Yep.
And we have morphisms, which starting from an object to another one with direction. We call that morphism. And then that is a rule. Let me make this category simple, just 2 dots. Actually, I need to work here. Another morphism. That is a rule that you must have a morphism as a composition of these two. So if I call this one A, B, and here C, then there must be a morphism come from A to C, which is equivalent. We haven't defined equivalent, but that's just a way of saying that this path is actually the composition of those two paths. That is the rule in the category. By comparison, in a category you have objects, and in functional programming you have types. As the lower level object, I'll explain why lower level. And you have morphism in category theory, and you have function in function programming. And then you have compositions, which is the same composition in function programming. Now, let's suppose this category is the category of a functional language. Then you're looking at different types here, right? So you're looking at, for example, you may have an integer here, and you may have a string here, and you may have a boolean. Just for example, right? In a language you have those 3 things. You have functions going through them, connecting them. And then I'll draw another circle here. You have 3 dots here as well, but here instead you have array of integer, you have array of strings, and you have array of booleans. Obviously, you know, any decent language can provide function for you to go from this to that and this to that, right? You can construct any function that you want to do this. And you have composition, that's the rule. Now, let's say if we can have a morphism, an arrow, going from this category to that category, that would be to say, it makes sense to say, hey, I map this into that thing, and this into that thing, and this into that thing. Right? This mapping, 3 of them actually doing the same thing, just putting the value for that type into an array. Yeah. Okay. But in the category, remember, in the category we have morphism, we have object, we have composition. This is not in a category, not yet. This is a cross category. So how do we describe this kind of you call it mapping? Is by shrinking those 2 circles to dots. You may have another category here, let's say promise of integer. Promise of string, promise of boolean. Now you would look like shrinking those 2. You will have a dot on the left and dot on the right. You have a category, and this category contains a morphism from here to here. Then, if you have another dot here, then you have the same kind of situation, right? This is the composition of these 2. Now those composition, by zooming out to make circle becomes dot, then you lose the information, obviously, because dot is the atom in, you can't break it down. But when you zoom out, it's the same thing. And we just give them different names. This arrow here is called a functor. We denote them using capital letters, because it maps between two categories. We can forget that because here we're in this category, we have the same arrow here. Just to give you a small taste, we're actually repeating stuff here. Right? It doesn't matter if you understand this or not, but we're repeating stuff. That means it's consistent. The composition, the rules you're following, is the same. You're just looking at a different level of abstraction. Whereas in object-oriented programming, every single rule, well, every single design pattern cannot be generalized to form this kind of thing. A note about generalization, this is not scientific, but you get a hunch when you look at so many things can be generalized into a very set of simple rules. That means you are very close to the truth. Because this thing works like this, another level works like the same way, another level works the same way. You kind of are thinking, I can describe anything using those simple rules, just onto different levels. So that's why composition is such an important thing in functional programming. So let's finish this one. We'll go to the node part. If these two things cannot convince you to go, functional, I have something else as well. Just looking into my notes, we can cut this one out. Okay.
Probably have a question.
Yeah.
What's the difference between compensation with the other M you just mentioned about the morphism? You mentioned about the M, the line which has the M. Yeah. So what's the difference between M and the compensation?
M is a function.
Okay.
In the category of types for programming languages.